Oh. Say my 10-second, hey, you're live. You'll be on Twitter in a couple hours, assuming there's something to be said here. I don't have any set agenda, and I reserve the right to moderate, never had to do it, and blah, 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 and compilers and whatever. Yeah. So for Jorn and Sid, I don't know if Sid can hear because nothing on. I had my son and my daughter-in-law show up day before late unexpectedly. And so yesterday morning, I had 2 extra adults in the house that I wasn't ready for, and we were visiting and doing stuff. And suddenly it was 10:30 and it was like, oops. So that's what happened. Life. It just went on. So does anyone have any question in particular, or I'll throw some, oh, hello, Syed. Am I saying that name right?
Yes, it's Sept. So
Syed.
Yes.
Close enough. Okay. Does anyone have anything they want to, any hotspot they want to poke at, or I'll throw something out there?
Throw something out.
Yeah, fine. So I'm doing a REPL, and there's and I'm only currently typing, which is fine. So I have strongly typed language on a REPL, sort of an odd thing. So if you add something in the REPL, it becomes known typed against all previous things and remains typable against everything that has to come after. And the typing story here is causing me to complain if I think there is ever a program which might cause you to fail typing, which in a REPL is not what you want. So like in the whole program model, when you're done putting code in, I know you're done, and I type it. In a REPL, I do this partial typing, and what remains has to be typable against whatever comes next. And what happens then is the default typing says, yes, there is a program you can write which will cause you to fail to type, cause your existing code to fail. It's not hard, actually. You just pass strings or ints are required or anything like that. It's just, it's stupid. So then
the current program is legal, but you could conceive of some change to it which would make it illegal, and that somehow makes
basically,
the current state illegal?
No. So I produced a piece of code that said, I'm adding 2 ints, or I'm multiplying 2 ints. Okay, but I didn't put any typing annotations on it. So I'm doing type inference. Well, the same program I can pass a string to. Well, I can't multiply 2 strings. So there is a set of arguments I can pass to this program you wrote that will fail to type. And that's not what you don't want to complain about it in a REPL. So the other version I'm at is, if your code is never used, it's dead, and then I don't care about its typing, which is kind of also what I don't want in a REPL. So you wrote some piece of crap code, and I successfully parsed it, and I recognized that there is an argument that you can pass it that will pass, and there is an argument you can pass it will fail to type. Both of these are true. And I want to say that's okay, that you only get an error in the REPL if I cannot type you. And let's see if I can get concrete here. This is where I threatened a long time ago to get Skype up because it has a better chat. So I just say some function is x, it's x times x, whatever. So here's the squaring function. Okay, fine. This function has arguments that will pass and has arguments that will fail. So if I do, that program then fails, but the fun itself is fine as it stands. Okay, so then there's another version of fun which it just fails to type because it's like crap internally. I don't ever call it. It's just, So here's a version where if I don't call fun, should I tell you it has type errors? If you ever call fun for any reason, the second version, I'm going to throw type error. Hey, you can't multiply something time to string. Would you like to get that reported first in the REPL, or when you actually call it in the REPL? Like if you never call fun, I don't care. You cut and paste a big old wad of code from somewhere else, you threw it in the REPL, then you started modifying as you went. A bunch of the shit you pasted in will never ever work. but you're not calling it because you didn't care. You just cut and paste from some interweb site. It's the same as JavaScript programmers do, right? You grab a bunch of crappy code from somewhere, you throw it in, you started testing what you're interested in. It passes, you're all happy, yay, and you carry on. And all the crap that you cut and paste in, 90% you never looked at, you never used, you don't care. And JavaScript's all good with that because it's lazy, it's dynamic typing, you never call it, don't care. So I have the general model which says if you don't call it, you don't care. Which brings me to the last version, the JavaScript version, which is you added a function that will never ever run no matter what argument you pass it. But you don't call it, I don't care.
That just kind of comes down to religious war thing, right? There's not a correct answer. There's just my preference.
That's exactly what I'm asking. What is your preference?
Highlight the error.
You like the error.
Like if it's always wrong, I don't see.
If it's always wrong, unless it's dead.
Even if it's dead, I would still highlight the error. Like if it's unquestionably an error, it's an error. But I do see the argument. Well, it's not an error because you're not calling it. But.
I have all kinds of grief for this kind of shit here. So a single assignment is a final assignment, and a colon equals assignment says I can assign it again. Right. So the first is a final. The second sets are all colon equals. So if I ever do a final assignment, and then I do another final assignment, you're only in error if you try to load from the second final assignment, because the rule on finals is that you cannot see a change in the value. So it's okay to assign x equals 2 repeatedly. The compiler will just take it like, oh, okay, fine. It's somewhere in the world I wrote some function where I wanted to have some temporary variable, fun equals something, x gets, let's see, it's bad syntax here. Oh, y gets, x times 2 and ... And I want to do something like this where, okay, y got finally assigned. If later I finally assign y again, but I don't actually, let's see, it's not a good example. I'm getting shit like I'm constant folding final assignments. Your second final assignment is crap. I can do this. So imagine this is in some giant complicated program with a loop. And, sys.print of y, whatever. So all I'm trying to do here is say here y should blow because it's trying to load from a second final assignment of x. And then I should complain and say no. But in fact, at the moment, I'm saying the second final assignment doesn't count. So x is 2 and an error. And y should be a load of an error thing, but instead y gets 2 times 2 is 4, and it prints 4, which is, and not, oh, you loaded from a final, from a second final. You attempted to finally assign twice and then use it. And that's not what I want. I want to actually have the thing blow on me. So I've gone through all kind of hoops on this one to make it work.
To make it blow on the second assignment rather than on the load?
Well, the report is on the second assignment. The blow is when you load from the second assignment. So if the second assignment is dead, so here's another whole.
Right, you're saying it's not an error until you try to use it.
Which exactly the same thing goes on with the prior funds. It's not an error unless you try to use it, which is exactly, it's implemented the same thing here. So I have this little partial program, x equals 3, x equals 2, x equals 3. No one loads from the second x. It's dead. I don't declare an error. And that was my intention. If you don't use broken code, it is not an error.
So it is, very clearly a stylistic choice, but I find it's interesting. Like I imagine in a larger program being forgiving of things like this, like reassigning something that's final. It's like it optimizes for the code writer, not for the code reader. And reading the code when I read x equals 3, not seeing that x actually equals 2, 10 lines up, I'm going to be very confused as I try to reason through with a value of x equals 3, when in reality that never happened. As soon
as you tried to load what x was, like you saw the final assignment, now find a use of it. And the answer is you can't find a use. So I hear you. You're saying that this is a confusing thing. The reason I'm headed down this path is support for portable programs that are sort of machine dependent and have if-defs. So type strong macros, if you will, where you say if-def Windows, if-def Darwin, if-def OS X, if-def Linux, blah, blah, blah. And in the if-defs, you have shit like wrong argument counts and unknown enums and things like that, error codes that don't make sense because they're on the wrong OS. And you want to just be forgiving as all hell and let it slide by. And so if you have an if of a constant folding expression above in the if quoted area, it's all dead. It has to pass the parser syntax, and after that it's just dead. And I don't look for errors. And that goal is to support the if-def, else if-def, else-if-def style. Oh, here's a late arrival. Kind of surprised we get people at all, given how how last minute this was. So this is good. Yeah, so once I have started down the path of you're dead, you don't count, it has this broad ramification. All kinds of things are dead, and all kinds of things just suddenly don't count. The obvious implementation for the don't count is that you're dead in the standard typing from standard use info, and I throw you out. That throws out everybody who's dead, and then you don't get errors unless you're using something that's illegal. And that brings around to the REPL, where you wrote some code and it's clearly dead until the next line where you use it. So at the time you write it, it's crap. At the time you use it, you get an error on the prior go. And I don't like that consequence. And I'm not yet willing to give up on you're dead, you don't count.
So it's unfortunate Cam isn't here today. So I've done a little bit of work with him on Ecstasy, and I think he tried to solve the same problem with the if-def style stuff. And I think he does something where he like evaluates all possible paths, like every version of the program that if-def will give you.
Right.
And so like they all have to be legal.
Right. And I went down the path of no, if you're dead, I won't. And obviously there's a limitation of how fast or how strong the compiler goes. So if it has to be textually obviously dead, it's the standard compiler. If I can constant fold it at typing time kind of rule. It's but if I can, then I'm going to say you're dead, and then I don't care. And that means I can have, alternative OS code on dead paths. And, the point of the if-def, else if-def is to wrap things such that when you're done with that sequence, you have a canonical useful interface that everyone else can now call independent of the OS. And that's how you get your OS independence. So I don't know. So yeah, right. So maybe I should bring this up with Cameron here, because I'm sort of like annoyed both ways. At the moment, I'm living with the how does it look if I let it roll on and then use it later? And the answer, of course, is I haven't got really big programs yet because I don't have a functioning REPL. I have a typing only REPL. And once this piece gets done, I'm going to work on execution engine, and then maybe I'll start to toy with bigger things, and we'll see how it goes. I hear you. You're saying the surprise late in life that this code can't be called, or this value of X got assigned, but it's dead, and so it's ignored, and it should have been final, and this should be the final value. And I look somewhere else, I'm expecting the final value to be 3, but there's no path from this X equals 3 to that other use over there, and it's only the X equals 2, right? And that's the sort of mystery you're claiming will make code unreadable in the large.
Yeah, it will make it harder. So if the code's hard to begin with, and then it got harder.
Right. Well, it's different. I'm hoping it's not hard to begin with. The syntax rules here are really stupidly simple. I have the world's simplest grammar. Not quite, but it's damn close to the world's simplest grammar.
No. Yeah, I'm saying if the program that someone wrote intrinsically
These
hard.
These are like things that the typing knows and is choosing not to complain about. And so an IDE could flag it.
So actually a question for you there on the type inference that's one of the things it probably won't be surprising given my other comments. I'm still not sure I like type inference because it's one of those things where I feel like if you've written correct code, then everything is good. But if there's something slightly wrong in your program, all of a sudden, like, the IDE can't infer your types, and all of a sudden, like, I'm reading somebody else's code and I have no idea what I'm dealing with. So in Java, I have this happen with lambdas all the time, right? Like, if the lambda wasn't typed exactly right, like, it doesn't know what it's trying to match, and I'm like, so I don't know what I'm trying to match or what the other person was trying to do. And it's like, again, it optimized for the writer. It was very easy to write, but it gets really hard to figure out as soon as something goes a little askew.
Right. So the writer can add the expected type annotations wherever he wants. So I expect type annotations, but if he chooses not to write them, then the reader has to hope that it worked. Well, it typed, strongly typed, so it worked, it typed. And
but in your language, it's like everything is inferred, right? Or you really don't have to specify, right?
That's correct. I can infer everything, and if you add an annotation, I will simply assert that it is correct. And you will get an error. If you add an annotation, 100%, you will get an error if it's not correct. Those aren't eagerly tossed. Those are correct or dead.
Yeah, so I'm curious how that, and I understand you haven't written large programs with it yet, but I'm curious if that, like, starts to become cumbersome as you have this, like, I guess, inferences building on inferences, and then you make one little change and all of a sudden the compiler doesn't know, like, it's forgotten what everything was.
Yeah, it's not that the compiler forgets, it's just it can't infer.
You can't figure, yeah, right.
Right. And I don't know. There's a, yeah, fine. There's a thing there that says you can add inferences. You can ask what the inferences are at any point by simply putting in an illegal inference. And then I'll tell you, oh, you're wrong, and here's the type it's supposed to be. And that's my inference type. And the IDE could totally do that as well, or have some variation of that if it wanted types, what the type inference tells you it is. But if you run a long time without types, this is a Scala problem. You run a long time without types, and it's all strongly typed, and then you get to a point where it falls over. Where do you go? I've done this with Elm. Elm's strongly typed too. And I run a long time, and I build a big thing, and suddenly it fails to type, and I'm like, what the fuck? And then it's giving me weird, bizarre guess types. So, oh, you were here at this type and that type over there, and those are all completely bogus. I'm like, shit, what? Then I go back and I add type annotations where I know what it's supposed to be, and now I'm still the writer doing this, and it tightens down where the error happens until I get it boxed in a little tighter. Then I usually leave those extra annotations in place so that the future fails mark it right. So there is a coding methodology that gets me there, a coding style that lets me, add annotations on demand or as needed.
So do you find that it's only things that are short in scope where you end up relying on the inference, and not when you have, say, a large method where you might be more likely to?
So some of the Elm shit I've written has gotten kind of large, and some of the up the level things I start leaving the annotations in. Yeah. I'm inferring all the small functions and the bodies of all small functions. And the top level ones, I usually put an annotation down because I want the documentation. That's a good point.
Right. Yeah, and I can see that compromise. Or again, going back to lambdas in Java, which are kind of meant to be short, it works. And where I felt pain from it not working, they tended to be larger lambdas that probably shouldn't have been lambdas.
It should have been broken out some other way. Yeah, right.
Yeah.
So same thing happens in Elm. You start using these nested functions being passed into map upon map upon map, right? And something blows, and then it's like you're all confused as to which is doing what. And then I start peeling them back out with a big old let expression where I put, here's a function, here's a function, here's a function. Okay, those are still blowing up. So here's a typed version of the function. And now I have them all well typed, and then here's the applications one after another. And suddenly, it makes sense now. But yeah, it's a good point. There's a nesting depth there before it becomes untenable. I had a panel with Martin Odersky about Scala and this very issue, and his comments were something similar. If you write a 200-line single line method that's got nested deep functions and applications buried in, no one understands it either. use bigger names and shorter functions and more annotations and more type inferences or whatever, and life will get better.
I wonder if there is a path in between by constraining the types just a little bit. So I'm thinking in the style of Haskell type classes or C++ concepts or Swift interface constraints, where you can do the thing that people did in Java and object-oriented programming, program to the interface. But we can also have type inference and have it compile time. So for instance, in Swift, you have protocols, and you can have that something is like a collection. And it's going to be constrained at compile time to obey the constraints of being a collection, but you can pass any type that satisfies these constraints. So it's kind of maybe in between, in that you have type inference, you have generic functions that can handle everything that obeys those constraints, but at the same time, you are not going to run into very deeply nested type inference and errors that can come with that. So it's kind of in between maybe. And it's kind of reminds me of this classical style of program to the interface basically, but with type inference.
So what you just said was duck typing, or what I heard you say was duck typing.
Well, duck typing would be like unconstrained C++ templates, because that's basically, if it acts like a duck, it is a duck. So for example, in unconstrained C++, so everything before C++20, you could pass a pair of iterators to a list and then to a sort function, but that doesn't actually obey the constraints that sort required, and you would get a huge spew, basically a backtrace entire telling you what exactly went wrong. And notice that the duck typing analogy is pretty good actually, because this huge spew that you get from C++ compile time error is exactly analogous to the backtrace you would get in Python at runtime, and Python does runtime duck typing. So it's exactly, there is a reason this error is this long, because it's not an ordinary compile time error. This is a real backtrace. So with concepts or with Swift protocols, you stop this at a certain point. So when you are offer of the sort generic function, you say that sort only takes sortable collections, period. And then you are not going to run into problems somewhere deep in the sort routine that you are comparing the iterators for less before comparable, which would fail for std list, and you would get this very complicated template error message that somewhere deep in the body of the function that you have called, there was a problem because the less than operator wasn't available for the pair of iterators that were derived from list. You would just get a list you have passed does not obey sortable container.
So sort should take an iterable that supports less than on the produced elements, right?
And for C++ sort also, the standard sort needs the comparison between the iterators, what you get from the iterators.
The elements that come out of the iterator, right.
Right, so it's...
I want to claim, let me think here. I want to claim I would give you a reasonable error because I would recognize you didn't have a less than on two, whatever you have. You have pointer to peoples and you don't say one's less than another or whatever you have. I'm trying to think of what I would do.
I think the point was that the error would be from like much deeper than you would think, right? It's not the thing you're passing into sort. It's 12 layers down where it tried to do the less than.
The point is it's also the iterators. It's also the iterators, not just the elements. The elements would make sense because you would think that the elements should be comparable, so you can use a comparison sort. But in the sort in C++, you also need the random access. So think of like array.
Yeah.
You have to be able to dereference this using the operator bracket, like index operator.
Right.
And single linked list or double linked list doesn't have that, but it's not going to tell you before C++20, it's not going to tell you that you have passed a linked list to the sort routine and sort routine requires random access. Instead, it's going to tell you this backtrace like error that somewhere deep you have tried to compare the address of the list.
You get the error at compile time or at runtime?
At compile time, at compile time.
Yeah, okay. Right, but you're saying that the error report is this very deep backtrace from
Precisely.
somewhere in the guts of the sort routine.
Precisely. It's exactly like you would get in Python for runtime duck typing, except it's for compile time duck typing.
And you would like to claim the error should show up at the application of sort to an iterator that didn't support random access.
Right, exactly, right when you
Yeah.
pass the list. And that actually will generate you a pretty readable error message that you have actually passed a collection which is not a random access collection. So you cannot use the sort algorithm that requires random access.
Right. I think by default, I would throw the error at deep in the sort right now. Claiming you've passed me a thing which doesn't have random access. And you'll get a random access, whatever. You go to error report deep in the guts of sort. And you could put a type annotation on sort that demanded the thing passed in support square bracket lookup. That's how I would claim that I'll solve it in my language by saying sort demands up front, and that only moves the error from deep in its guts to its ABI interface. And that's actually probably that's a good coding style. I don't know how to enforce anything like that. So the stylistic issue is simply to say, I have a public available API. I have requirements come from deep in my guts. Some of those requirements are exposed at the API. I can throw the stack trace. I can throw the type fail error message from deep in the guts, or I can throw the type fail error message at the API boundary.
And I think it's kind of nice for documentation purposes to have something at the API boundary, because the programmer reading the interface to that also understands, okay, sort requires random access collection. Now it's clear, as opposed sort requires the less than operator to be available at compile time for the iterator that is a nested type of my collection. It's like a little bit more understandable interface, I think.
Right, and actually, the error you'd get might include bits and pieces of the iterator that's pulling a value out, coupled with the I didn't find a random access. Yeah, fine. I think for usability, I'd claim you have to put a type on the sort, just what you said, sortable collection. But if you don't, you would still get a correct typing error, but it would be in the guts of sort, which, yeah, can get big. Yeah, no, I don't have any, I don't know, sounds good to me. I don't have any other thing to think about there. I'm still seeing error messages in funny places for me too. So this goes back to what we talked about earlier. I do a sort, do a sort, and if you don't ever call it, I don't care that it works or doesn't or has type errors. Pass the random bad collection in, then you get the error message. So this is the question we had. I don't know, some people came late here. The REPL was playing around with the REPL. When do you throw an error message on the REPL? In my case, I throw error messages when you use a thing you've defined in the REPL, not when you define it. And that has, you know, pros and cons. Oh, what? CVS, I've seen this guy before. And late. Fine. Well, one more late arrival. So, hello, yeah, we're stumbling around. Oh, he's connecting audio still. Yeah, it's fine. Well, we're at a sort of natural conversation break here. Hi, welcome. We were just talking about when do you report an error message and how do you report them, and type inference, hiding types such that when the error message does show up, it's hard to interpret. And you know, what if anything is to be done about it? And oh, it's a natural break in conversation. So somebody throw something out there, or I'm gonna have to come up with something else here.
So, yeah, question for you.
Yeah.
And definitely well, I guess it still falls into the realm of compilers, but as the industry moves kind of in the direction of ARM processors, I'm curious what you think, like, I guess, how hellish will it be? Like all the existing programs that are silently reliant on the x86 memory model.
Oh God. Yeah. So, gosh, unfortunately I went through that experience a couple of times. So I did the Itanium port, and we found plenty of folks who matched the Java memory model, failed the x86, required the x86 memory model, and while matching the Java model would fall over, and did it again at Azul. So twice I saw many Java programs which were correct under the x86, fail under the Java model, which wouldn't show up until you ran a weaker memory model than the x86. And you had to figure out what to do about them. Some of the people I talked to went and fixed their bugs because they were, project proud of, we have a cool thing we're doing, and yes, of course the bug will fix it, but you had to wait for the fix to come out before you could go sell product, right? Some of the people were like, get the fuck out of here, we're busy. And then you had to
decide. So they were saying, make your Azul run like an x86?
Well, there was no easy way to do that. You put fencing every fucking place. x86 put fencing in because they started from the model and they were trying to be backwards compatible when they went multi-core long ago, dual core motherboards. Like I guess a third time, went through the era where there were motherboards were manufactured, dual CPU socket motherboards were manufactured not by Intel. So the memory model varied by motherboard manufacturer. So I had a Compact and a Dell, and they had different memory models, and we didn't even have a name for it back then. We just knew that this one died and this one didn't. And you screwed around a little bit left and right, and this one died and that one didn't, right? And it was, that was the realm before we knew what the fuck to do. And then Intel would refuse to put out a memory model because they didn't want to be responsible for all the motherboard manufacturers. And which I kind of get. And that didn't change until they basically would put out complete multi-socket chipsets, and everyone was using them. And all of the off third brand, motherboard manufacturers quit doing their own interconnect chips and took Intel's. So there was this long transition period where you could still get Asus or whoever would have their own chips for the interconnect, and fuck it, who knew what the memory model was? And then after it was well established that everyone was using Intel motherboards, sockets all the way, Intel announced effectively, and this was like now 10 years ago, but there was a good 10-year window where multi-core were everywhere and Intel was refusing to say what the hell the model was.
It's got to be longer than 10 years ago. Right? That had to be. You're saying 10 years ago this was up in the air?
Right. I want to say Robert Morgan did a talk where he talked about the Intel memory model. I finally ensconced it somewhere. I have a link to it lying around. I can go find it. He gave a talk somewhere. It was first public announcement from Intel employee of here's our memory model. But yeah, it's a while ago. Fine. Okay, so then there's the Intel model. The Java model predated that. Because I was doing, there was no Java model. We had a discussion and we said, okay, this is the model we want. And the Java model was driven from high theory. So there's a lot of discussion of a little bit of backwards compatibility and a lot of high theory. And this is the model we have, right? We know we can make it go fast and it says something reasonable. And there were a bunch of PhDs that went around that's finally settled out. And we had a model. Okay, it had nothing to do with anyone's hardware. So we had to go bridge everyone's hardware to the model. Oh, I see. On Apple Silicon? Well, what's Apple Silicon?
That's just ARM64. That's just ARM64.
Okay.
AR64. So it's interesting that it's even possible. So they have this Rosetta2 translator, which is similar, if you remember Rosetta, the original one that was for migration between PowerPC and x86. And now they are going from x86 to AR64, so Rosetta 2. And apparently there is actually a flag that enables TSO semantics, which is a strong memory model as in x86. And now this program makes it possible to enable it for an arbitrary process. And I think it's interesting that it's even possible. I mean, surely it's going to have an overhead, but it's still.
Well, once you're designing the chip, I think it's not getting more conservative isn't too hard if you're willing to give up performance because you expect it to be transitional. You scrape every ounce of thinking and effort into getting performance, and a lot of it's tied up around the memory model. Okay, fine. If you then say, well, fuck performance, I want a conservative model, it's not hard. But you fuck performance. Intel has it do it both ways. They have to have the conservative model and performance, and they throw $1 billion worth of engineers at it to get that to go. But ARM can say, yeah, it kind of sucks if you turn on TSO, but it'll work. And that's a good transition model. Now fix your TSO bugs and then turn it off. And if you can turn it on and off sort of rapidly, like per process basis, that's kind of cool though. Because there'll be some folks who will be very slow getting it to go that people are excited about for many, many years, backwards compatibility. Yeah, Apple can do that, I guess. I have a flag on the process saying this is an old one and it's transliterated and needs TSO and blah, blah, blah. And it'll stay that way until we get a new version from the vendor. And maybe we do, and maybe we don't, but we have control of the ecosystem. So we know for a fact it's TSO ready or not.
Yeah, and for transition, this may be actually pretty good because I imagine going for entire code base that was made on x86, assuming strong memory model, and now finding all the places where that assumption was wrong, maybe a bit non-trivial.
Yeah, those bugs are subtle.
And the TSO enabler is part of Rosetta. So that's the code then that it's translating was code written for x86 and being dynamically recompiled for ARM. So it would seem
they're claiming a special register.
Enabler.
No, it's more. They're claiming a special register. This is on the ARM processor. So it's a software hardware co-design. Rosetta 2 is probably emitting certain classes of fences in certain places. And also we put the ARM processor in a special mode.
Right, but my point was if the intention of Rosetta is to take x86 code and run it on ARM, right? Like clearly the x86 code was written for the TSO, right? Like you'll have to turn it on there. But it's interesting if they also make that available for code that was written for ARM or just, say you're running a JVM and so it's been written for ARM, but the Java code it's running wasn't written for ARM.
Right. And you could still have x86 code, which happens to be okay without TSO.
Right, it's single threaded, I guess would be
it's doing GUI shit. It's fooling around, has very little background to none. It's fine right away. It could still have background stuff and be totally fine if it wasn't going hog wild. The places where you fail is when you have a tight high volume handshake between threads. And that's not a common model in a lot of zones. You run movie codecs, maybe you run audio things, maybe you run stock ticker market things, maybe I'm running a GUI that's doing whatever, maybe not, I'm doing a file manager finder thing, maybe not. So I'm doing a text editor, I'm doing an email editor, I'm doing this and that, maybe not. So a lot of these things could be
I guess fine. So with your experience with Azul, most programs were just fine, even if they kind of did expect the the x86 memory model?
The big framework applications had the fails because they were expected to run lots of threads under heavy load with arbitrary code. And they tend to all fail, which is a crucial business case for us, right? Otherwise code typically up and ran. And so we had these big, horribly complicated, it's only horribly complicated things that blew with running lots and lots of threads. And then we get all kind of weird errors and you have to go sort them out. Some of them were tolerable and they turned into transaction fail retries that were, bogus. But you just retried and it worked. And some were intolerable and you had to go sort out what happened. The core framework threw a null pointer exception is what it came back as the common fail mode. And it threw it in a bad way and then it fell over and died. And so you had to, why did you throw a null pointer exception here? Well, I got a null here. Well, that was totally legit by the model. Yeah, but we weren't expecting and yada. Somebody had to have a volatile or a lock thrown in a funny place. As I mentioned before, those guys kind of, sort of, typically would take the, bug fix from Azul, but we can't bug fix everyone else's multi-threaded code. So it was an issue. I think that the right answer is, the seamless transition, and it's a little slow. And I guess you're all happy if your ARM chip has low power and much better battery life. So you took the ARM and you're living with it. And then you go back to the vendor and say, we can't turn off TSO or it dies. But if you turn off TSO, you'll cut your battery power in half, right? Your clients might like you to turn off TSO. So fix your bugs. I think that's Apple's doing the right thing there. I didn't realize they were doing an ARM chip.
I think it's supposed they're supposed to have a laptop out maybe the end of the year with their own ARM chip, basically taking from the iPad Pro, like the next generation from that. Okay. And I think they're saying that it'll be like as powerful as the current MacBook Pros. So
they have to recompile, really? They'll have to recompile all the common stuff. I assume it's also going to have sort of battery life out the wazoo.
Yeah, pretty extreme battery life. And this is like, I don't know how closely you follow Apple stuff, but like their thinnest, like Ultrabook, the discontinued 12-inch MacBooks that were so ridiculously thin, those will be what they'll reintroduce that on an ARM processor, and that's supposed to have performance as good as their current high-end MacBook Pros. So if it actually happens, it would be pretty amazing.
No, I didn't know. I don't have an Apple. I don't carry any Apple products. I don't use Apple. I don't know. I don't follow Apple. It's all good. I got
presumably everyone else will follow. So you'll end up with an ARM laptop running Windows. Not too long after.
Fine. Maybe. I do gaming on my. I guess I want lifetime and gaming on my laptop, and that's sort of incompatible. About 6 years ago, I got the longest known battery life laptop at that time, which is actually, I still have it. It still works. It's a fine laptop. I got 8 to 9 hours if I wasn't gaming, 3 hours gaming, plenty long enough to go sit in a conference all day without ever touching a power plug. Then I got this behemoth, which for a gaming laptop as a replacement, new, modern, much better graphics, blah, blah, blah. Draws too much power for the standard power outlet on an airplane. So if I'm doing an over the puddle hop for 12 hours in a seat, it pops the breaker every time I plug it in. I cannot get a charge on a plane. So it fails in an hour for no battery.
That's got to be a little scarier in flight too.
Oh no, every seat has a circuit breaker. All independent from each other. I have popped them dozens and dozens of times trying to diagnose. Surely it can't be this one. Surely this airplane is different. No, they're all the same. They all have the fixed cap. I'm all well over the cap. Bang. I actually bought a separate power charger that's much, much slower, that draws a lot less, that I can now take on a plane. But I had to take a couple plane flights, transatlantic plane flights, before I realized that was a fail and it was just never going to work. And I just had to go fix that. No, the plane's engines and electronics and shit are completely safe here. You cannot hurt them by plugging in your overcharged whatever into the seat power. They're pretty good about it.
I contend it would still be scary. Independent, fine, but yeah, I don't know. I don't want any hardware issues anywhere on a plane.
On a plane, that's not a hardware issue. That's the point. The failure is the safe, normal case.
That's true. Okay.
I learned this from the hardware guys. Like, there are no errors in hardware chips. All states are just states, including error states. And then you have recovery states or this state or whatever, but you just have states, and that's what it is. And so there are no errors in that sense, not in the classical, what you think about an error. It's just another mode the hardware's in before it gets back to the mode that you'd like it to be in. And so, like, with doing this typing game, I'm doing this horrible typing algorithm. Of course, things are mistyped all the time, and I have to carry the mistypes through until maybe I get the typing sorted out. So error is the normal case, and they all start out in error, and I gradually lift the types until I discover I have a valid typing. It's all errors are normal. It's a different mindset, maybe.
Yeah, it reminds me. I had a thing years ago in C++ where I worked on this library that would put out like beautiful Java-like exceptions, like full visible stack traces. And the first customer that we gave it to like called us saying it was crashing. It was like, oh my God, like this thing was it was supposed to be Java style, like friendly, like it can't crash. There couldn't be a seg fault. And so they reproduced it, and there was just a beautiful exception on the screen. See, it crashed. I'm like, no, 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 that's not a crash. That's like gorgeous. Look, you have a stack trace. It tells you what you did wrong. My program didn't crash. It was, you put in the wrong thing, and I gave you a beautiful error. But yeah, from their perspective, it crashed.
Yes. Yes. Well, that's an expectation setting issue. I'm an old school C programmer. I expect Crash to give me a OS command line prompt. Bang! Oh, back to the OS. Oh, fuck it. Now I got to whip out a debugger or something. I don't know. These Java exceptions, they're so pretty. What the hell? Yes, I have to have Java
as we get ready to restart the school year, my daughter's taking a programming class, and I was really curious. Like, I've been teaching her Java, and she's going into 10th grade. And I was like, oh, what language are you doing? And I was really surprised to hear the answer of C. I'm like, okay, like things are about to get real.
There you go. In high school, really? In
high school, in the very first intro to programming class, the teacher's doing C. And as I thought about it, I'm like, okay, there's a lot that's really good about that.
Yeah.
Like not starting with objects and methods and virtual, like just like functions are so simple and structures are so simple and core dumps are so simple.
Yeah. I mean, I grew up with very, very simple machines, and I understand the hardware and the machine model because of that, you know. And then I talked for many years. I've talked to people who so indirected, removed from the core hardware, they just didn't have a clue what was going on under the hood. I give them that damn, you know, under the hood of a modern x86 talk more than a decade, and it's still a popular talk. And it's just like, okay, guys, you are so far removed.
Again, to go back to the kids, when my kids ask me certain things about the computer and I get embarrassed when I can't answer, like at one point my daughter wanted to know how, like, you hit a key on the keyboard and what makes it show up on the screen. I'm like, oh my God, yeah, that's like, I can't even begin to explain that entire path, and it seems such a basic question.
Yeah, my first sort of seriously good programming was a Radio Shack Trash Z80. And, you know, you learned about keyboard interrupts. And they even fed you the damn XY coordinate from the two-dimensional layout on the key and the interrupt, and you did the table lookup. And you didn't have to.
It
was baked into the BIOS.
That's what I started with. And
yeah, you could get that.
The Trash 80, that was a fun machine in my high school computer lab, where that's what we had. Our instructor had built. He used a VCR as our mass storage device, which always impressed me. We also had an actual hard drive. I think it may have been 5 megabytes hooked up to a Trash 80.
Yeah,
just, wow. An infinite amount of storage.
Yeah, I had a cassette tape drive. Cassette. Oh my God, that was it was slow.
Yes.
Why are you here? Hang on. My cat is demanding something. Unfortunately, he's not very communicative, so he'll get annoyed at me because I'm not giving him what he wants, and he'll leave in a minute. x86 microcode. Oh, microcode disassemble. Rep any with a multiply negates the product. That's probably not a hidden feature as much as that was just a leftover how the wires crossed. Huh. Nice. Okay. There you go. Such a, I don't know, Intel, they did all kinds of such a weird thing and kept going with it. The whole, let's add some prefixes. Like, really? As a thing? Fine. Yeah, I kind of assumed, RISC was going to sweep the world, and x86 is going to die off, and that would be good. And that didn't go. The world didn't go that way.
But in the end, the x86 is RISC underneath, right?
It is now. Oh yeah. They took all the learnings.
No.
They robbed.
I would disagree. So basically, x86 is HPS. HPS is the high performance substrate by Yale path. So if you heard about modern branch predictors, for example, so this is the fundamental concept. HPS introduced the idea that you can take complex instruction and break it into micro operations and dynamically schedule them out of order to execute on multiple execution units. So if you hear about micro operations out of order and superscalar, this is what we have thanks to HPS. And what is interesting historically that Yelpat did it basically because he did not want to follow the path of risk. So in a sense, what we have today is the anti-risk. And the distinction matters in practice because if you think about this, many x86 instructions are not simpler when you break them into micro ops. In fact, some of the micro operations are even more complex. Think of fusion, for example. If you have x86 instruction sequence, when you first compare and then you jump, so you compare one register with another, and then you jump if not equal. Those are two x86 instructions, right? And then you have translation into fused single micro operation. So you can have micro operations that are more complex than the x86 instructions they come from. So this is not RISC. This is not in any way, shape, or form simpler or more reduced instruction set.
Yeah, I think what was meant here by saying it's RISC actually is that even in those reservation stations, the format of instruction and operands very, very much like RISC, right? So you have 3 operands like destination, source, and in some cases you have 4th operand, but yeah.
Well, no, because they can be even more complex than x86
yes,
instructions.
yes.
So I think that kills the concept. I know it's a popular, I think it's a popular misconception.
How many load and store, how many uses of the load store unit per micro op?
Oh, you can have micro ops with multiple. Again, you can have one-to-one translation for x86 instructions, which is a load op, which is a load and operation. And you're going to have the micro ops that are paired to that instruction. So it's not necessarily simpler.
No, I was asking how many times the load star unit gets cycled per micro op. Are there micro ops that do multiple load star unit references in the same micro op?
There might be some instruction which occupies several entries in load buffer, for example, or several entries in store buffer.
When you say combine several entries in a load buffer, you mean like a misaligned load crossing a cache line is broken into 2 independent loads and then refusing, or?
Actually, I meant occupy several entries in load buffer. Yeah, not necessarily it should be unaligned, but it depends on the instruction, right? Because of if you do those kind of complicated addressing in the instruction, it definitely might be
the complicated instructions on the addressing modes never add more references to memory. They just do more register ports to go add, subtract, multiply, divide, and then you get one memory op.
Oh yes, you're right. Yes, it just allocates more registers, but yeah, memory reference is always one. But
specifically asking about the load store unit getting cycled, like the move ops might try to do a load and a store or have a cycle baked in or not, or what, you know, misaligned move from x86 move instruction.
Yep. Yeah, we always can think about return, right? It's load and no, not return, call. It's always store and load at the same time.
Yeah, I was trying to come up with, is there more than one? Because the usual story is that you went to one, that was part of the risk gained away from VAX. As opposed to, you know, going under the hood and tormenting everything else after that. Then what you basically, I heard you say is, you know, the micro ops are more like VLIW almost. It's whatever you can fit and wire the hardware, you know, back and forth. And we have a translation step. And then you run the parts out of order and do what you're gonna do with them. It's all good. From a compiler's point of view, the x86 these days is fairly RISC-like in that it's 2 or 3 addresses, all registers available for all things. The encoding is like bizarrely Baroque, fine. Ignoring the encoding, you got 16 registers, one's a stack pointer. You have 15 other registers, everyone can do everything, fine. it's reasonably sane. You have all the half split registers, which, where'd you go, Kat? Fine, quit talking to me. You have half split registers, which mostly you don't care about anymore.
64, I think x86 in a sense got cleaner, or AMD 64 compared to the.
Oh, you can get way the hell cleaner. I'm just saying, if you're writing code for an x86 from a compiler's point of view.
And the register amount, I think it's still at 32-bit era, it was pretty register starved, but with 64 bits, I think that got much better.
I generated Java code for the 32-bit 8-register machine. I want to say I tried it at 16-bit, but I think we gave up on that. So 32-bit 8-register machine, completely register starved. When you went to 16, it took the big chunk out. Well, then go outside, Cat. Quit bugging me.
I'm thinking now how would JVM, that would be amazing to have JVM running on 16-bit x86.
It's whatever the compiler did. It's a big C program, right?
Right.
So mostly you had address space issues. And we did the split the heap up from the code space from whatever, but it wasn't big enough, and we gave it up. It was going to compile, but it wasn't enough space. So the very first version of HotSpot with C2 is like 1.2 or something. 1.3 is the first released one. Internally, 1.01, 1.2, things in those numbering ranges would run really, really well under a megabyte. They would come up and run spec JVM 98 in like a handful of megabytes. It was really tiny. It was all good. It was much later that it just kept blowing up in storage space. So the minimum Java launch, is whatever, 250 megs. I don't know what the hell it is. It's pretty big now. Back in the day, yeah. 640K, who needs more? Yeah, but for running efficiently and well for less silicon, I can imagine ARM won't have a problem here. And the JVM will port to ARM easily. Everything else has to be screwed around with. Trying to think about, is there another fun thing between, like when we did the ARM version of Java, we went back and forth with the ARM guys a bunch on how to get the memory model compatible. I think they went through a couple rounds of memory model changes until they could emit the Java model efficiently and well. They had some new model things they came out with way back in the day, still at Sun, it was a long time ago. And we went over it in fine detail, and we're like, this is really weird, and misses a bunch of stuff. And we went back to them, and I think they went around a few go rounds and settled out on a slightly different model that you could implement well on Java. You can implement Java well on.
Is ARM's memory model weaker than Java's?
Yeah, well, most of them are different. So like Intel's is almost strictly stronger, as you would expect. In a few weird corner cases involving final fields, you have to deal. And then obviously load store bypass, everyone has to deal. Everyone else who's not running that, it was clearly different. Like I did Spark TSO, which was not the same as x86 TSO. It was similar enough, but it had some fail modes. And then Spark had a weaker model that you could turn on that no one ran in because it was too weak, no one had to code to it, but we tried to get the Java to go to it. And now you needed a bunch more fences because it wasn't thought out well enough. Azul's was hugely weaker than the Java model, but we thought about it really well, and you had fences in particular places that were acceptable in exchange for, it mostly ran faster because you didn't need fences everywhere. My experience was no one got purely a sub or superset of the Java model. It was always misaligned, and you had to go do something in some case. There's a load store bypass is the obvious big one, but you could still have load bypass and store bypass, and depends on what people were doing. Final fields have their own grief. You have custom zeroing things you had to think through, because you had to independent of what the Java model says. I can't hand you an uninitialized anything. So if I do a new and I publish the pointer, and then I begin filling in the final fields, the act of publishing the pointer meant that at best, you're going to see zeros. You better not see anything other than zeros. You'd like to see stuff after the constructor, but if I publish in the constructor, you better at least see zeros. So you better have zeroing, fencing, and then doing that. Well, that means every new has to zero and fence. Well, that gets really expensive if every new has to fence.
And you're not able to prove whether it's published before.
Right. So then you ask,
constructing.
Can I then go and prove in the JIT? It has nothing to do with the Java type system. Can I prove in the JIT that you didn't publish? Or can I stall your publishing pointer print for some duration of time, but I have to stall until I have to put a fence out, or I have to have some other fencing arrangement. I have to have some fencing arrangement for the zeros. x86, because of its strong model, you don't do anything, you just put the stores. And you put the stores first. The zero stores happen before the publishing store, and you're good to go. And they make that fast under the hood by throwing gobs of silicon at it. Itanium, you had to put like a store release or whatever between the last zeroing store and the next publishing store. And Azul, we had a cache line 0, and which has a 0 line. It had a built-in fencing thing. And the hardware carefully did the right thing for that store versus the next publishing store. So the fence was typically cheap unless you did unless you evicted a, how did this work? You evicted the cache line. How did he do that? They did some hack there where they watched it, and if you never evicted the publishing store out of your cache, it didn't matter really. But if you evicted the publishing store to the cache, he stopped and he pushed out all the 0 stores that he had pending and finished them off before he let you publish. So you basically got a stall on publishing store. But yeah, you have to think hard about that situation, and I don't know what ARM's done there. There are some cool things you can do. The Azul cache line 0 let us not ever read memory that we were going to zero anyhow. You had to have a system-wide cache evict event that everyone knew that they couldn't have a copy of this cache line because you were going to have it in yours. But no one ever sent you their dirty bits, and the dirty bits never hit memory. You just zeroed in your cache. And you didn't read from memory. They just zeroed in your cache. And the big trick with that one is that it cut out 1/3 of your memory bandwidth. A big, busy Java program running, 1/3 is reading dead memory that you're going to zero anyhow. This is on x86, 1/3, and totally measured with ICE systems and everything else. Completely, obviously there. 1/3 of your memory, 1/3 of your bandwidth is consumed reading memory you're going to zero anyhow, and you don't care for those red bits. And 1/3 is writing memory out that is dead already, and the GC will collect it, and you'll never ever use it. And 1/3 is like active shit going back and forth because your caches are limited in size. So kind of a crazy thing. We use that cache line 0. We took 1/3 of our total memory bandwidth costs away. It was useful. And ARM could do the same thing. We tried to get Intel to do it, and they weren't having it. ARM could do the same thing. It's a little tricky to get right. It's not that hard. If you get it right, big savings. A bunch of people tried and got it wrong. IBM for sure, Power has got it wrong. You can't, because the fencing's not correct. So after you zero, you have to still wait on a fence. You have to take an expensive fence and wait. You have to get the fencing right. Looking at the microcode disassemble, like, what's the trusted computing thing on Intel chips these days? Until they have like some horribly complicated thing going on. Okay, say it. You didn't say anything because of sound.
SGX?
There you go. That's better.
Yes. So you asked about trusted computing?
Yeah.
SGX, and they just released a few weeks ago new white paper about TDX, trusted domain execution. So it's going to be very much like S&P from AMD, I think.
S&P from what?
From S&P, secure nested paging. So it's like you encrypt everything in domain of virtual machines, and the memory is encrypted there. So neither host nor other tenant VM has access to keys, to encrypting, decrypting keys. So TDX will be based on multi-key total memory encryption technology of Intel, as far as I understand by white paper. And yeah, I heard that SGX implementation will also be relying on TDX, on MKey TME, on total memory encryption. So it sounds scary.
Are they doing all memory this way, or are they just doing the keys?
So how SGX worked, they had limited EPC, right? You could, you had 128 megabytes per machine, and you could use it and distribute it to different applications. Each application would have each key to encrypt, decrypt. And yeah, SGX2 version 2, I think, had much more memory. I'm not really sure how much, what was the limit, but
Is it on the same die, or does it just have another memory port and memory chip off die?
So it's working, as far as I understand, just on the, so before caches, before data gets to the L1, right? Before, yes, in L1 everything is decrypted. In L3 everything is supposed to be encrypted.
So they have an address space where in and out of the address space it's entirely encrypted, and decryption happens between L3 and L1.
Yes.
And what's the decryption key?
So this is like it's not really clear how SGX is implemented, right? I mean, actually there are a lot of side channels attacks which are stealing keys based on, for example, cache out. There was a paper about how they do you remember MDS attacks? So every time data got evicted from L1 through a line fill buffer, they could use line fill buffer as a source of injection to the transit execution control flow. So they could steal encryption keys in this way. They could like restore 80% of data which was encrypted. So you still can leak it somehow, but yeah, how it's implemented, at least I don't know for sure.
Okay, fine. Yeah. I don't know, it's just one of these big, nasty rat holes. Sounds like it'll be only driven by, how to say it here, construction laws are written in blood. You know, people are going to have to get burned bad, and they'll demand, and then we'll get a better answer, and then the crooks will get a better answer, and we'll get somebody get burned bad, and you know, a lot of money will change hands before the effort goes out, which costs a lot of effort, money to make the effort too. So maybe that's just the trade-off.
Yeah, so I can add something on the trust execution environment, at least from Intel side, because I'm working in a startup which is doing exact same thing.
Excellent.
Yeah.
What's the startup called?
It's called Scontain.
Scontain. Okay. Throw the name in the chat if you're up, if that's where you're at.
Okay. Okay. Yeah. Not for that. Just. So if you have some clients who are aware of their data when they upload it to the cloud, so this platform basically taking care of putting everything to SGX, Intel T.
Mike's live, Matthew. Sorry.
Yeah.
Yep. With slow waking kids. We're all on coronavirus vacation time.
Yeah.
What modern times, right? What the hell are you gonna do?
Some question. I mean,
yeah,
it's not really about compilers, but just wanted to hear your opinion. Maybe somebody dealt with it already. It's more about linkers. So let's suppose I would like to keep all static relocation information, even in linked executable. It's like usually we have static relocation and dynamic. Dynamic are about shared libraries, and static are just.
I lived this era, I know.
Yeah, yeah. So, and the static are just in object files, but when I have linked executable, of course, they are lost. And is there any way to keep them?
That's up to the linker. There certainly was an error at a time when you could throw a flag and that data would just carry through.
Okay, yeah, but I mean, at least I didn't see anything, any option in modern linkers to.
Yeah, I don't.
To pass it through.
I haven't stared at that sort of thing. I certainly knew of its existence and ability back in the day. I did linkers for companies as part of compiler work, and there was a flag to support that said pass that shit through.
Okay.
Whatever. I don't know what people are doing these days. GDB being GDB, GCC being the eldest of these things that have been around forever and a day and backwards compatible forever and a day, you could go ask them. Linker flags out the wazoo, and that guy, he might not. I don't know.
You mean keep all the same offsets from the old?
No. Just keep the data.
Yep.
Keep the relocation data.
Okay.
Right. Usually part of the link step is you merge everybody and then you change the relocation for the post link world. Some of it you keep around, some of it's dynamic, some of it still static in case that's how the placement goes. But bulk of it has all been re-smashed together and doesn't need a relocation between itself anymore. But you could keep it per object file. There's no reason not to. And other than space, right? You look back in the 70s and 80s, it was space. Of course, you didn't keep it if you didn't need it. Just slowed things down. And of course, in the land of JITting, you do all that shit when you're making the code on the spot. And of course, you toss it on the spot. But you actually have it for a while.
Yeah.
I JIT code into a randomly allocated buffer that gets reallocated from time to time as the code gets bigger until it's done getting JITted, and then it's moved into the code cache. So it gets moved 4 and 5 times ultimately. But then once it's installed in the code cache, toss all that shit. Exact same reason. So yeah, I don't know, I'd go ask an old linker.
I think it's still kept nowadays though. At least I've seen garbage collection code actually looking at the code blob which still had the relocation data in the JIT or in HotSpot.
The kind of relocation that's kept has changed. A lot of it is tossed. What's kept is static addresses that if you move the code, you have to change the static address by the delta, and the location of all the objects that are in the code, because the GC has to relocate the objects in the code directly. And then there's like backtrace tidbits. So there's a bunch of stuff. It's called relocation info. It's not what Said's saying is relocation info. Not all of it. It's different. It has its historical backgrounds and that kind of stuff where you have an x86 instruction. If it's a jump, the offset's okay when you move it. If it's a call, it's a fixed address. So if you move the call target, you have to change the bits of the call itself. So that call has address bits in case its target gets moved. And so the relocation info was pointing at the call saying that target reference from this call. If I move that code, I have to hack the call. That's okay. So now that information's around. When I take a wad of code from here to here, some of the addresses internally within the code had to be updated and some did not. And so when I moved it once the last time and never moved it again, I tossed those things. But I kept in the wad of code for Java, I kept, where do I find the pointers for GC? Where do I find de-optimization points for stack trace calculations? Where do I find all the register to memory layouts for every call? So if I have a call instruction, an exception gets thrown, and I'm going to go unpack the stack, and I have to go look where the thing is at the call site, which is a de-op point. I have a mapping from, just like debug info, I have a mapping from register to where it landed on the stack. That's all called relocation information. Now, in the land of C, you call some of it debug info, and some of it relocation, some of it static, and some of it dynamic. In the hotspot world, it's all just relocation. So you have to watch out for the naming change.
Okay.
And it's different stuff too. Some of it's the same, some of it's different.
Yeah, I remember seeing something, maybe I can look up the code as well, but I remember seeing something with regards to relocation info for virtual calls, interface calls, optimized virtual calls, and or some extra data attached to that for method handle intrinsics.
As soon as you have a call site, you have to have stack unpacking info. So where did the mapping from the Java architected state land on the x86 stack? You had to have, if you had a static address that the optimized JITted code said, this is a virtual call pointing at that piece of code over here, but I de-optimized that piece of code because it was now illegal. This call can't jump to that code anymore because it's illegal. So there's a transition step where I go to this code and I patch the first op to say, go to a cleanup, but then I come back to this guy and I patch him to say, quit going over there, go to the cleanup code. You know, and you can't get rid of this blob until you patch all these sites here. So maybe hundreds of these in the code cache. The code over here has to hang on to the first instruction being, you know, don't touch this code, it's bad. Go to the cleanup until you patched all these. Those are done in a GC cycle. So until you pass a GC cycle, you can't free the storage for the old JITted code. So there's all kind of lifetime management shit going on code cache because of the direct things point to each other. The other one is this guy calls that guy, and x86 can pick this up, instruction up, and put it in his iCache and his internal, you know, decrypted IOPS or whatever the hell, do something else for a long time, and then come around and finish executing. You can't know that you've seen the last touch of this guy until every thread runs through a save point. There's all kinds of fun games that go on about when I can say I can get rid of this guy or get rid of that guy that are non-obvious and lead to lifetime nightmares. But you definitely have to track, you know, all the code offsets, whether it be a static call, an inline cache call, or a you know, variation thereof. There's like 4 or 5 variations thereof. Interfaces typically jump to an iTable stub that's not going anywhere. So the interfaces weren't an issue. Inline caches had issues, and static calls have the same issue for that one.
Okay, it makes sense. Yeah.
Yeah. There's another ones like locking had the same thing for not the same thing. Locking has similar things though. You can block at a lock and expect to de-opt. So locks have the de-opt info lying around. They didn't have the cross cache, cross compilation unit issue, but they definitely had a I'm blocking, I'm locking, I'm throwing up an exception now. That's a fun typing thing I want to sort out through here as a type ergonomics. This function call and all its nested friends takes no blocking calls, or it does. And tell me if it does not. I want to know, because if it blocks, I want to do something different. Like my GUI wants to know that it's not getting the main GUI thread blocked. Why is there only one main GUI thread? Because it's too hard to block and not block or whatever. It's just reactive programming, you know, that's why reactive programming came around. But there's a way to do this in the typing system where I could say, yeah, it's safe to call because it's not going to block, or it is. Well, it's an hour and 20. We've had a good run. I'm happy everyone showed up. Thank you for coming on the last short notice. My life got busy yesterday. That's what happened. This Friday, I'll try again to do it on Friday at 10 at the usual time. And any last words, or I'm going to wrap it up?
Yeah. See you next week, hopefully.
Yep. See you next week.
Yep.
All right, bye-bye.
Thanks, Cliff.
Bye.